In this video, we're going to cover these vocabulary words that you may have had in your earlier science classes, but we just want to make sure you have them down 100%. The first two things we need to kind of cover is chemical and physical properties. Okay. Now, you might not have a lot of ideas about chemical properties because you haven't done a lot of chemistry experiments. So we'll talk about that second. But physical properties is something you should be able to completely get. Okay. So a good definition of a physical property is anything that you can observe or measure. Okay. So if we're talking about my shirt that I'm wearing today, if we're making observations or measurements on it, you can see it's a short sleeve shirt. Okay. It's a Bengals shirt. It's black and orange. Okay. All these things that I can observe about the shirt would make that a physical property. Now I could measure some things, okay? I could take this off and put it on a scale and get its weight or its mass, okay? That's something that I could measure. I could calculate the surface area, I could measure that. So those would be physical properties that are measurable, okay? So anything that you can observe or measure would qualify as a physical property. To be a chemical property, you gotta know a little bit about the chemical that you're talking about, okay? So a chemical property is its ability to form new substances, okay? For example, hydrogen has the ability to form water, okay? Now, obviously hydrogen is in water and that's why it has this ability, okay? So you do need to know about chemical reactions and chemical experiments to really fully understand, chemical properties. A lot of people just like say, oh, it's flammable, okay? But that's nice, but that's kind of like a memorization piece where through experimentation, you get these experiences and you start to learn more about these different chemicals that we're gonna come across in chemistry, okay? Now, the second bullet point is probably one that you're more familiar with. However, there are some misconceptions that I see that pop up with students, okay? So the second bullet point is chemical and physical changes, okay? Now, a good definition or rule to use to differentiate between a chemical change and a physical change is a new substance or did the composition change? So if you are forming a new substance or the composition changed, okay, that would lead to a chemical change, okay? If the chemical composition did not change or you did not form a new substance, okay, then it would be a physical change. So the thing that I see pop up, okay, is some people say that one is reversible and the other is not. I have often heard that chemical changes are irreversible, but physical changes are reversible, and that's actually false, okay? They both can be reversible and they both could be irreversible, okay? So it just depends on the change that we're talking about. So let's go into a few examples to make sure you kind of fully understand that, okay? So I got a bottle of liquid water right here, and I have a refrigerator in the back storeroom, okay? So if I take this bottle of liquid water and I put it in the freezer and wait a day, and I go and take an observation, this liquid water would then be solid water, or what we call ice, okay? Well, the composition did not change, okay? It's still water molecules, it's just water molecules now in the solid state, okay? So since the composition did not change, we would say that that's a physical change, okay? Now let's talk about reversibility, okay? In order to be reversible, we have to do the exact opposite of what we did before in order for this to be reversible. So if on day one I went back in to the back storeroom, put it in the freezer, and I waited a day, we need to do that reverse process, okay? Which means getting it out of the freezer and bringing it out and waiting a day. That would be the reverse process. And indeed, it would change back into liquid water. So this would be a physical change that is reversible, okay? Well, let's talk about a physical change that might not be reversible, okay? I got a piece of paper here, and if I tear it, okay, did the composition change? Okay, no, they were paper molecules before, and they're paper molecules now, okay? But is it reversible? Okay, remember, to be reversible, I have to do the exact opposite. So I kind of made this motion when I tore it, so let's do the opposite motion, which would be going up, okay? And as you can see, it did not go back to its original form, okay? So this is still paper though, so it is a physical change. It's just an irreversible physical change, okay? So this idea of reversibility is a terrible rule for talking about chemical or physical changes because it just doesn't exist, okay? We have chemical changes. Okay, what happens if I took this piece of paper and I lit it on fire? Okay, it was paper molecules initially. Okay, but as this burns, these paper molecules are now ash molecules. Okay, those are no longer paper molecules. That's ash molecules. So this is a chemical change. A new substance is being formed. Okay, it's irreversible. I can't take that ash and make it paper again by just doing the exact opposite of what I did. Okay, and you'll learn later, like in like I think we have like 3 chapters in AP Chemistry that are dedicated to reversible chemical reactions. So we have some chemical reactions that are irreversible, like the paper burning, okay? But we got 3 chapters at the end of our textbook that talk about reversible chemical reactions that work in equilibrium. They work forward direction and the reverse direction. So once again, the reversibility rule, it's terrible. It's not true. It's a myth, okay, that has been created somewhere, and a lot of people think it, and I just want to kind of break that myth, okay? And then I want to substitute that with a good rule is, did you make a new substance, okay? Did the composition change, okay? If you did create a new substance or the composition changed, it's a chemical change, okay? If it did not, it's just a physical change. A couple of vocabulary words that give people a little trouble because I don't think they've seen it before they've taken AP Chemistry or college level chemistry is this term extensive and intensive. And I have a mnemonic. I don't think it's a strong mnemonic device, but I match up the E of extensive with the E in enthalpy. I'm gonna grab a better marker because that didn't show up well. Let's try that again. And what enthalpy is heat energy. And I'm matching up the E in enthalpy and the E in extensive to kind of get you to remember that enthalpy or heat energy is an extensive property. And what I want you to kind of think about is gasoline burning in a fire, okay? If I take a drop of gasoline and put it in a fire, you'll get a little bit of heat energy, just a little bit, okay? But if I took a gallon of gasoline and dumped it in a fire, I mean, that's actually pretty dangerous, okay? I would get huge amounts of heat energy, which tells you that the amount matters. 1 drop, just a little bit of heat, a gallon, like probably way too much heat. So the amount matters. So an extensive property is where the amount matters. So enthalpy, heat energy, mass, you know, the more stuff you have, the more mass you're gonna get. That depends on the amount. Volume, the more I pour into a bucket, you know, the larger the volume, so the amount matters. Okay, so enthalpy is an extensive property, and extensive properties are where the amount matters, okay? So you might be saying, well, I can't think of anything that's intensive where the amount doesn't matter. And the one that you'll see most frequently, especially at the beginning of the year, is density, okay? If I have a drop of water and measure its density, it's gonna come out to 1 gram per milliliter. And if I took a gallon of water and measured its density, it's still gonna be 1 gram per milliliter, okay? So the amount does not matter when it comes to measuring density, because density is an intensive property where the amount does not matter, okay? Next 2 things is filtration versus distillation. They are both separation techniques. The way filtration works is using some type of medium, okay, that has holes. So if I created a grid with my hands, okay, that could be a filter, and it would allow any particles that are smaller than the holes in my hand, okay, to fall through, and then my hands would catch everything else that's larger than the holes in my hand. And that's the way filter paper works. That's the way you know, sand filtration works. You know, things travel through these holes, okay, and the smaller particles make its way through, but the larger particles do not. So it's separation by the size of the particle, okay? Distillation is a separation technique as well, okay? But it's using boiling points, okay? For example, if you have one substance that's at 100 degrees and another substance that's at 200 degrees, well, if you heat that mixture up to 100 degrees, the stuff that has a boiling point of 100 degrees will turn into the gas phase, okay, and separate from the stuff that doesn't boil, that has a boiling point of 200 degrees. So both of them are separation techniques. One is by size of the particle, the other one is by use of the boiling point. But they're both separation techniques, and they're both done physically. This is not chemical separation, this is physical separation. And then lastly, we have units, okay? We're gonna be doing a whole bunch of conversions, okay? And the conversion factors that you have to memorize are from tera all the way down to pico. And you'll find this sheet in Google Classroom where you can print it out.